The next test we're going to look at is the integral test. So we're going to let an be a sequence of positive terms. We need that sequence to be represented by some function that is continuous, positive, and decreasing over the interval. And if that's the case, then if the series from capital N to infinity of the sequence and the integral from n to infinity of the function that represents that sequence are going to behave the same way. So they're either both going to converge or they're both going to diverge. Now the things you need to remember about this test, dogs cuss in prison, that just stands for decreasing, continuous, and positive. And we need to know that this does not mean the series converges to the value of the indefinite integral. All it means is that they behave the same way, so they either both converge or they both diverge. So let's look at an example. We have the series from 1 to infinity of n over n squared plus 1. So this is the function that represents our sequence. So we want to check to make sure this function is decreasing, positive, and continuous. And it is for all values where n is greater than or equal to 1. And you can analyze that on your calculator if you like. So it means the integral is going to behave the same way. So we're going to take the integral from 1 to infinity of n over n squared plus 1. So this is going to be the limit as a approaches infinity of the integral from 1 to a of n over n squared plus 1. We're going to use u substitution to integrate this, so we'll let u equal n squared plus 1, which means that du will be 2n dn, which means that dn will equal du over 2n. So we will have the integral of 1/2 1 over 2u du. When we integrate that, we'll end up with 1/2 ln absolute value of u, which is going to be 1/2 ln the absolute value of n squared plus 1. So now we have the limit as a approaches infinity of 1/2 ln absolute value of n squared plus 1. We're evaluating that from 1 to a. So this is going to be the limit as a approaches infinity of 1/2 ln absolute value of a squared plus 1 minus, we'll plug in 1, that would be 1/2 ln of 2. We'll substitute in infinity, which would give us 1/2 ln infinity squared plus 1 minus 1/2 ln 2, and this is going to go to infinity minus 1/2 ln 2, which tells us that this integral diverges. So since the integral diverges, that tells us that the series is going to diverge. So we can go ahead and conclude, therefore, the series from n equals 1 to infinity of n over n squared plus 1 diverges by the integral test. Alright, so let's look at this example. We have the series from 1 to infinity of 1 over n squared plus 1. So here's our function. We need to check that that function is decreasing, positive, and continuous, and it is over the interval where n is greater than or equal to 1. You can check that in your calculator if you like. So that means that the integral from 1 to infinity of 1 over n squared plus 1 is going to behave in the same way. So this is going to be the limit as b approaches infinity of the integral from 1 to b of 1 over n squared plus 1. So when we integrate 1 over n squared plus 1, we get tangent inverse. So this is going to be the limit as b approaches infinity of tan inverse of n evaluated from 1 to b. So this is going to be the limit as b approaches infinity of tan inverse of b minus tan inverse of 1. So we'll plug in that infinity. We have tan inverse of infinity minus tan inverse of 1. Now as the value inside the tangent inverse approaches infinity, the tangent inverse is going to go to pi over 2. tan inverse of 1 will be pi over 4. So pi over 2 minus pi over 4 will be pi over 4. So the integral from 1 to infinity of 1 over n squared plus 1 converges to pi over 4. So that tells us that the series is going to also converge, but it doesn't necessarily tell us that it converges to pi over 4. It just tells us that it converges. So we can now conclude that the series from 1 to infinity of 1 over n squared plus 1 converges by the integral test.